Okay, so talking about the friction and forces mini lab, because you collected actual data, it's not something that was given to you. All you have to do, and I say that with a sarcastic look, all you have to do is figure out the coefficient of friction, static and kinetic for each of these. How hard could that be, right? So the first thing to do, obviously, is to write, and I did say all this yesterday, but I'm going to repeat it because we'll just do it at one shot. First thing to do for each example is to write your expression for the coefficient of static friction, if we're working with static friction. And, then realizing that you don't have either the force of static friction or the normal force, you have to calculate that. So if you were one of the groups who heeded my suggestion and did a zero angle, your first one's really, really easy, because if theta is 0, if this is our force applied, this is our force of static friction, this is our normal force, this is our force of gravity, we can do a sum of forces on the x, which if this thing is not moving, the sum is 0. And if that's true, the only two forces on the x are the force of static friction, the force applied. They're opposites. They have to be equal and opposite. So we know that force of static friction, or the either way you want to cut it, equals the negative of the applied force. And so there you have something you can put in there. Do a sum of forces on the y. That's also 0 because it's not rising into the air spontaneously. That would be really cool if that happened someday. It hasn't happened yet. And the only ones we have here are force of gravity and normal force. Negative of the force of gravity is equal to normal force. So now you've got something that you can put in there. Okay, fantastic. As long as your angle theta is 0, this is all you have to do. So for your first set of calculations, that's it. For your first set of calculations, if you have a 0 angle, and we're talking about the kinetic example, let's do that. No. Copy. Paste. Okay. So if now we're talking, instead of static friction, about kinetic friction, first thing you would want to do is write your expression for the coefficient of kinetic friction, Fk over Fn. Okay. Well, again, same thing. Sum of forces on the x, basically just is a way to prove to yourself that, well, actually, let's back that up. If this thing is moving at constant velocity, what's the sum of forces on the x? 0, because your acceleration is 0. So that was the whole key to having constant velocity. So we've got 0, and the forces we have here are the force of kinetic friction and the applied force. They're opposites. So, whoops, Fk has to equal the negative of F applied, or vice versa, whichever way you want to cut it. And same thing on the y, it's not rising spontaneously or sinking, so we have Fg and Fn, and they have to be equal and opposite. Okay, so that's pretty easy. This is if you had the 0 angle. Now if you didn't have a 0 angle, if you opted to not do one that was at, well, I mean, you had to do multiple angles, so for whatever your angle theta is here. In this case, we have normal force, we have the force of gravity, and we'll start off with the static example. We have the force of static friction. Well, here's your force applied, and that's now divided into an x and a y. So we have the force applied x, which is equal to F applied cosine theta, and we have F applied y, which is equal to F applied sine theta. Okay, so far so good? Okay, this is not the trickiest part. So if we're going to do the same thing we did with the rest of them and start off by writing our expression for the coefficient of static friction, mu s equals f of s over f of n. Okay, so now we're just down to getting expressions that we can use for f of s and f of n. Let's start with f of s because it's on top. So that would be our x-axis. So sum of forces on the x. Again, this thing's not moving, so sum of forces on the x is 0. And all we have here is the force of static friction and the force applied, x. So that's pretty easy, not a whole lot of trouble. So the force of static friction has to be equal to the negative of the F applied x. Okay, great. We have something that we can put in there. On the y, it's a little bit trickier. And this is where the sign thing becomes a bit of a struggle. Let's get that up there. There, we'll do that. Okay. So we know this is 0. That doesn't look like 0. That looks like some other Greek letter. There. Okay. We know this is 0, and we know that what we have are the force of gravity, the normal force, and the force applied on the y. And we know this is down, this is up, and this is up. Conceptually, what we know is that the force of gravity has to be equal to the sum of these two. Okay, does that make sense? And I think that's the easiest way to think about it conceptually. I know a few of you have been saying like, just, make this one, subtract them. Don't do the add negatives, which is an option. I'm trying to do the whole have faith in the algebra thing, which some days is harder than others. But what I was finding to be the way that I made fewer mistakes doing this calculation was to first just set it up for myself mentally to say, oh, okay, well the negative of force of gravity has to equal the normal force plus the force applied y. Okay? And if I do that, and again, this is sort of my brain at work, what's then evident to me is, oh, okay, well then I can take, I'm basically putting all the down forces on one side of the equation, all the up forces on the other. Well then I can say, oh, well the negative of the force of gravity minus the applied force on the y is going to be equal to f of n. Okay, and if I'm trusting the signs, then this ends up being a positive number from which I am subtracting a positive number. So then our normal force is less than gravity, which is true. Does that make sense? So as long as the force that you're applying on the y is being applied upward, which it is, your normal force is going to be less than gravity, because the floor isn't having to exert all the upward force on your object. You're exerting some of it. You're doing some of the floor's work in essence. Does that make sense? I will warn you on the calculations for this lab, when I say that this is to get you really good at doing normal forces in instances of funny applied angle forces. Last year they kind of blew it off, and I had video of myself explaining all this to them, and I think one group actually did the calculations right, and I went through and I made a key for every single group and graded their calculations. Boy, was that a pain in the tuchus. But I think you guys are all on track to do these right. I'm seeing good calculations so far. Questions on this? We can talk a little bit later about the conceptual question of what if the applied force is down, then the normal force is greater than gravity. But let's wait on that, I think. Okay, good? You got time to work. 4D, bridges, and friction and forces mini lab. That's it.